IoT device security isn't an option. Device developers must ensure their products are protected from attacks, are safe and secure through the manufacturing process, and able to be managed securely throughout the life of the product. This is even more critical with the acceleration of artificial intelligence and machine learning model deployment at the network edge. Here to offer a solution is Philip Attfield, Chief Executive Officer of Sequitur Labs. Philip, over to you.
Hey, thank you for having us. Grateful to be able to present today. I am Phil, one of the founders and the CEO of the company. My background goes back into everything from silicon design and validation through to cloud-connected systems. So we've been at this a while, and I think sort of one of the greatest opportunities we have is to actually provide what we have in terms of spanning a lot of difficult problems. So we'll discuss some of those. So a quick overview on Sequitur Labs. What the company is about is protecting high-value embedded devices, so internet-connected devices, from being compromised. We primarily address, say, industrial markets, such as machine vision, building automation, smart home, but sort of every type of connected device. And so a common underlying theme is that these all provide critical operations that needs to be managed through the life cycle of the device. We do this through a product called the EM Spark Security Suite. It's a software product only. It's basically a set of firmware, tools, and APIs that system builders integrate into their system when they're going to develop and release a product. We support a wide variety of microprocessors, so call these ARM microprocessors, from companies from Microchip, NXP, STMicro, and NVIDIA. So we're seeing some disruption at the edge. Biggest challenge is that applications are now being migrated, say, from back-end functions onto edge devices. And implementing security, it just isn't an option. So when a solution provider goes to build out a system, they're faced with this new technical problem of how on earth do they implement security? There are features in silicon that need to be dealt with. It requires a very deep understanding, down to literally, reading through thousands of pages of data sheets to implement correctly. And then on the other side of this is where their application needs to integrate with the cloud. They have all sorts of other challenges dealing, for example, with API stacks or the interfaces that would allow their applications to communicate with cloud backends, securing those, and then also dealing with the content management that goes back and forth. An area that we're seeing that's actually critical and, say, evolving quite rapidly for us, it's quite exciting, is the protection of AI and ML models, so artificial intelligence, machine learning. This is actually very interesting in terms of companies that are rolling the products out now realize that there's high value in those assets and they need to be protected. But where does this all begin? It begins with the supply chain. If you're going to connect a device to the internet and it's got to be a managed device, then this goes back to the very beginning of the provisioning and manufacturing of the device, and then carries through into the operational life cycle or the business processes. So that in some instances as well, we work with the customer, or there's a need to work with the integrators to sort of augment their business processes and call it their software development and firmware handling procedures, because all of this now has a security flavor to it. And given that the system developers, nothing's changed for them. They still are under the same constraints, pressure constraints they were before. They have a budget to meet. They have time credit. Basically, they have time to get the device onto the market. And they still have the same. They basically still have the same team with the same expertise that they had before, and they may not have time to figure out all of the security details. So in order to secure the device, we take a holistic approach. So we basically call it secure by design, and it's securing chip to cloud. We start with basic essential functions such as secure boot, so that the device or the system only runs authenticated firmware. And this means that all of the boot components, all of the boot firmware through to the operating system and through to the applications, and select applications are authenticated, so full attestation. We also configure the silicon so that there's memory isolation, and in some instances, there's actually hardware isolation. So for example, storage devices or certain classes of critical functions that need to be isolated out properly. We then provide mechanisms that allows anti-piracy. So this is in general around applications or content, but in the case, for example, and specifically relating to AI and ML, those models are actually protected, and this is done by the company that developed them or the operator of the systems themselves. And then once the system is in the field, we provide the lifecycle management functions. So critically, secure over-the-air updates, and this is the situation where only authorized devices can actually perform the update, only authorized devices can use the firmware. We provide failure recovery in the boot chain, so in case there's say a partial update or a failed update, the system will recover automatically. And then we also leverage advanced capabilities in the silicon to provide threat metrics. Say, for example, if there are physical tampers and a cabinet is open, we report those, but those are trusted transactions as well. So you have a high level of assurance on the information that's coming out regarding security events from the device as well. So the architecture that we leverage, if you look on the left, it's actually, consider that being the microprocessor. And we leverage a feature available in our microprocessors called Trust Zone. This allows the creation of two separate domains. On the left-hand side, we have, let's say, for example, Linux. This is where system integrators or builders would build their normal application stack. On the right-hand side, we have a secure enclave. And in there, there's a set of features that are available, call those the critical security functions. They're leveraged by the regular Linux applications and the normal world applications to perform the critical secure functions. The benefits are that you have the applications themselves change very little, if at all, and they make use of hardware isolated functions to perform their most critical operations. So on the right-hand side, we list off some of the features. So from anti-piracy through to the provisioning and all of the mechanisms we described earlier. So protecting AI and ML models at the edge. This is interesting. So previously, it was that these models would run in back-end systems, but given the amount of data and the throughput required, the functionality is now being migrated to edge compute appliances. And given that there's typically no human operators in front of these devices are fully remotely managed, and this presents a whole host of challenges. And these applications are out in the field. When you consider the companies that have developed the models or the algorithms, they've invested millions of dollars. This is their intellectual property. It's critical for them to protect that investment. And how do they do this? So this presents all sorts of challenges. So what we've done is basically take and we apply the features that we provide software to basically give them the ability to isolate and manage the models themselves. So sort of at the very basic level, we make certain that the models are authentic and we hide the models or protect the models from attack. So isolate those so that they can't be attacked on the device. So what does it mean to actually protect the device, to protect the model or the application? The software features required mean that an AI or ML model should be encrypted and locked uniquely to each device instance. In other words, if a system is hacked or compromised and the model is lifted and there's an attempt made to use it on another system, it will never work. It comes off in an encrypted form, and the key is cryptographically bound in the secure domain to the hardware itself for that specific processor instance. So it raises the bar very high for piracy. So we basically provide means for, call it the publisher, to create an encapsulated application, and we provide a loader that will load that application on the device. So all of this is an integrated system. The only change for the developer is instead of pushing clear text or a clear text application down to the device, they submit it through a tool that basically sets it up to be locked to each device instance. And then at the time of loading, the applications are decrypted using the keys that are unique to that device. They're loaded into whatever the intellectual property, or call it the AI ML engine, is resonant on the device, and interacts with the Secure OS to basically run the model. If we want to go further, it's possible for customers, if they have an algorithm that they consider very sensitive and they don't want to run it in the normal Linux or untrusted operating system, they can actually write their own trusted applications and have those interact with their models. So this gives them the ability, in some instances where if there's a need for a proprietary system where it's highly valuable and they want confidentiality even on the execution, they can write their own trusted applications that interact with the model. So this goes to sort of the ultimate level of protection for the application. And then once the application is finished running, obviously all of this is removed from memory. So like any other application, it's gone from the system, and in the secure domain, there's explicitly wiped. And that pretty much concludes what we wanted to cover. Hopefully this is beneficial, and appreciate your time. Thank you very much for joining.